morning, Professor Cinzia Casagrande from the University of Torino will continue her lecture series on Fano manifolds and the Lefschetz defect.
Thank you. Okay, so good morning, everybody. So I promised to start the lecture with an example of flip. Okay, so we take X to be a P2 bundle over P2. This is O direct sum of 1, 2 times. So this X is a toric fourfold. It is Fano. Has pK number 2. And it is a P2 bundle over P2. Okay. And so it has a special section that corresponds to the projection onto O. Of the vector bundle onto the trivial summand. And so this L is just P2. And one can see that it has normal bundle, the direct sum of 2 copies of O of -1. So it's a negative. Okay. And in fact, this X has a small contraction. So this is, of course, elementary because the pK number is 2. And the exceptional locus is L, which is contracted to a point. Okay? So this X has pK number 2, and it has 2 elementary contractions. One is the P2 bundle over P2, and the other one is a small contraction. Okay? So I want to describe the flip of this F. And to construct the flip, we blow up L. And then because of the normal bundle, the exceptional divisor will be P2 cross P1. And one can check that the normal bundle of E in X hat is -1, -1. Okay? So in fact, this is the exceptional divisor also for the blow-up in another direction. So this blow-up contracts E to P2, but you can also have another blow-up of X hat. So you can realize X hat also as the blow-up of a curve with exceptional divisor E, which is contracted to P1. So there exists another map from X hat to X prime, which is the blow-up of a smooth curve, L in X prime, so X prime is still smooth. And this has still exceptional divisor E. So E is contracted to P1, so this L will be a smooth rational curve, and the normal bundle of L in X prime is the direct sum of 3 copies of O of -1. And in fact, I can tell you what is explicitly X prime. X prime is again a projective bundle, but now over P1. So X prime, this new fourfold, this diagram is all toric. This new fourfold is a P3 bundle over P1. So we have a diagram. Okay, so we have X had this contraction over P2, the small contraction, and then we blow up and we blow down. And in fact, X prime also has a small contraction to Y. And the exceptional locus is just the curve L. And G of L is a point, okay? And so this will be the flip. Since the exceptional divisor is the same, this is a birational map, which is an isomorphism in codimension 1. So we just replace this surface with this curve. And so here again, L will be a section of the P1 bundle, and it corresponds to the projection onto the trivial summand. So X prime has this P3 bundle over P1. Okay. So again, X prime has pK number 2, and we are describing the two elementary contractions. And okay, so X is Fano, but X prime is not Fano, but it will be log Fano. In fact, it's toric. And it's easy to see that it is not Fano because, so you have this normal bundle here. So it's easy to compute that the intersection of the canonical class with L is 1. So minus k cannot be ample. And instead, so here you see that the relative cone of G is generated by the class of L. So this will be k positive. Instead, if you take a line in this P2, one can check that its intersection with minus k is 1. And the class of this curve generates the extreme array corresponding to F. So we see that the flip changes the sign of the intersection with the canonical class, okay? And also I wanted to remark that this small contraction has one-dimensional fibers, but it is not divisorial, because we cannot apply that result that we saw because it is not k-negative. I also want to make another remark. In this case, we do the flip and we stay smooth. This is special because we are in dimension 4. But in general, when you do a flip from a smooth variety, you get a singular. You can get a singular once. And, but for Fano fourfolds, basically, this is the only type of flip that you can have. So if you start from a Fano fourfold and you do also many flips, you always get a map like this. So you replace a smooth rational surface isomorphic to P2 with a smooth rational curve, and your fourfold stays smooth. And all these exceptional loci will be disjoint. Okay? And this is very useful in dimension 4 because you start from your Fano fourfold, you do flips, and you stay always smooth. And this makes life easier. And starting from dimension 5, it's false. Okay? So are there questions on this example?
So you said that in dimension 4 this is the only flip for Fano.
Yes.
Is there a classification of flips?
No. No, I don't think so. But already you can write in dimension 5 also toric examples where you get a singular. But I think there is no classification. Yes. Yes. So basically, So the classification of one flip from a smooth fourfold k-negative flip is due to Kawamata. And then if X is Fano, you can see that if you iterate, the exceptional loci do not touch each other. So it's always the same description. Okay, then let's go back to our general setting. Yes, because as I wrote, the vector bundle is NEF but non-ample, and so the relative O1 will induce a small contraction, I think, in both cases. Yes, right. Other questions? Yeah. Okay, so let me just recall that what we are doing. We have our Fano variety, which is smooth or of arbitrary dimension. And for any prime divisor, we are considering N1 of dx, which is the image of N1 of d inside N1 of x. So it will be the linear span of classes of curves that are contained in D. So its dimension is at most the Picard number of D. And we have introduced an invariant of X, the Lefschetz defect, which is the maximum of all possible codimensions of these linear subspaces where D varies among all prime divisors. Okay. So we discussed a little bit of this invariant. Basically, we are interested in prime divisors where this subspace is small. And I want to discuss the theorem that if the Lefschetz defect is at least 4, then X is a product of a del Pezzo surface with another variety, with another Fano manifold. Okay, so, and the strategy. So let's fix D. And at the beginning, we don't need to ask anything, and then we'll see what we get. We fix our prime divisor. So I said we want to consider extreme arrays that have positive intersection with D, because we want to mimic the strategy that we did in the case of where D had a Picard number 1. And so we run an MMP for minus the divisor D. This is just because in the classical version of MMP, we consider extreme arrays having negative intersection with B. And then we said last lecture that the MMP ends with the divisor becoming NEF, the divisor B becoming NEF, if and only if B is numerically equivalent to an effective divisor. But here, clearly, D is minus a prime divisor, so it can never be numerically equivalent to an effective divisor. So the MMP will end with a fiber type contraction. B. So let's see what we get. So we get a sequence of varieties and birational maps. where so every xi is log Fano. And then, so for every I from 0 up to r minus 1, so up to the last step before xr, there is an extreme array, Ri, extreme array of xi, such that it has intersection, positive intersection with di, and this birational map, sigma I, from xi to xi plus 1, is, so we have two possibilities, depending on, so this Ri will be birational, so a birational extreme array. And it can be divisorial or small, so it is, sigma I is the contraction of Ri if it is divisorial, if Ri is divisorial. Okay, and in this case, remember that we take as the new divisor, it's push forward. So in this case, di is a prime divisor, and what we have to observe that it cannot be the exceptional divisor of this contraction because it has positive intersection with the extreme array, while we say that the exceptional divisor always has negative intersection with the extreme array. So di is different from the exceptional divisor, so it's never contracted. And so we just take its image, and we still have a prime divisor in xi plus 1. Okay, so this is the divisorial case. Or in the small case, sigma I is the flip of Ri if Ri is small. And then we just take a di plus 1 to be the transform of di. And so we have a prime divisor in every xi. Okay, so this is all the steps, and what do we get in the end? So in xr, we have this prime divisor dr, and then we have a contraction of fiber type that has positive intersection with dr. So there exists f from xr to y, elementary contraction of fiber type such that this prime divisor dr has positive intersection with the extreme array associated to f, positive. All right? And then let's start from the end. So since the dr has positive intersection with the extreme array, it means that it has positive intersection with all contracted curves. So it must meet every fiber. So this means that it dominates y. And so we consider the push forward. Okay? So this is a surjective linear map with one-dimensional kernel. And inside here, we have the N1 of dr xr. And since dr dominates y, this also must dominate. This is an argument that we have already seen. I take a curve in y. I can find a curve in dr which is sent onto that curve. Okay? And then we don't have many possibilities for the dimension. Okay? So today we will see a lot of linear algebra. As Jenia told us, it's very easy. So the codimension can be 0 or 1. Okay. And now I want to see how the codimension of these subspaces associated to the DIs vary along the MMP. So maybe let's just call Ci the codimension of N1 of dixi for simplicity. So this is CR. Aha. Let's see how. So we study one step, and it can be divisorial or small. So let's see the divisorial case. So in the divisorial case, sigma I is an elementary divisorial contraction. Okay, and then we consider the associated push forward. And again, surjective linear map with one-dimensional kernel. And in fact, so here we have di, and di plus 1 is just its image. Okay, and so the N1 of di plus 1 in xi plus 1 will be just the image of N1 of dixi. Okay, so how the codimension varies depends whether this subspace contains or not the kernel of the map. Let me write here. Okay, so we will have that Ci plus 1 will be either Ci or Ci minus 1. Because the ambient space, the dimension drops by 1, and the dimension of the image can be either the same or can drop by 1. Okay? And so this happens if and only if the kernel is contained. And this happens if and only if the kernel is not contained. Otherwise, say. Right? But then this kernel is a line, and it is the span of the extreme array. Which is a half line. So this happens if and only if this is equivalent to asking that the extreme array is contained in N1 of dixi. Okay, so in the end, we have the following, that Ci plus 1 will be Ci if the ray is contained in N1 of di xi, and Ci minus 1 if the ray is not contained. Okay? Now, this is the divisorial case. And then in the case of a flip, exactly the same holds. And I leave it as an exercise. Show that the same holds when sigma I is a flip. And I will maybe just give a hint. So in the case of a flip, you have to consider the two small contractions and just remember that you have that di has positive intersection with the small array, and then di plus 1 will have negative intersection with the small array. This is just a hint for the exercise that you have to use this. Okay, other questions? So let's sum up what we did. We start with some codimension, C0, which was the starting codimension of the N1 of the X. And at the end, we get 0 or 1. And at each step, either it stays the same or it drops by 1. Okay? So it means that there are exactly, let me call this S, that will be C0 minus CR, so it can be C0 or C0 minus 1, depending on what happens in the end, steps where Ci drops, okay, which means that the extreme array is not contained in N1 of the xi. So these are the steps that we are interested in. Okay. And then let's see what can we say for this situation. Excuse me? Yes, more or less. But yes and no, because I could a priori have one-dimensional fibers, but the array could be contained in N1 of. So this implies, let's fix a step be such that Ri is not contained. So we have our map. So Ri is always birational, because we are not considering the last step. And let's consider its contraction. I'm using another letter because if Ri is small, then they are different. If Ri is divisorial, they are the same. Okay? And for sure, so remember that we also have that the prime divisor has positive intersection with the array, but the array is not contained here. And this is the situation we studied in the first lecture. So this implies that phi is finite on the divisor and has fibers of dimension at most 1. Okay, so let me just recap what we did. We started with a prime divisor. We ran an MMP for minus D, so we consider extreme arrays that have positive intersection with D. And we still have a prime divisor along all the MMP. In the end, we have a fiber type contraction. So we saw that in the end, the codimension of this subspace can be only 0 or 1 because dr dominates Y. And then we studied how this codimension of N1 of the prime divisor varies. And we saw that in both cases, we have these two possibilities. So we have, if we started with a prime divisor where this C0 is at least positive, we have a bound on the number of steps, a lower bound on the number of steps where this happens. And these are the steps we want to study. And now let's study them. Okay, so we have this birational map with fibers of dimension at most 1. So I would like to be happy and apply the results that we saw in the first lectures. But there are two problems, that xi may be singular, and the result apply when xi is smooth. And also we need it to be the map to be k negative. Otherwise we saw that it's just false, that the map must be divisorial. Okay? And so problem. Xi can be singular, and phi does not need to be k negative. So let's address the two problems, and we start with the second one. So far we almost did not use that x is Fano. If x were log Fano, we could have done exactly the same. And now, so we use a very nice idea from the paper of Birker, Cascini, Hekon, and McKernan. So for k negativity, use the, let me just write and then explain, the MMP with scaling. So of course, we are just using the idea in a simple context, in a simpler than BCHM. So what is this idea is that when I run an MMP, if I have an ample divisor in my X, it is always possible in our situation to choose an MMP in such a way that all the extreme arrays have positive intersection with this ample divisor. So remember when we talked about MMPs, I insisted that we had a choice at each step for this extreme array. So this ample divisor serves like a way to choose. It's a prescription. And in this case, of course, we want to use minus k. So here we really use that x is Fano. And yes, of course, at the first step, it's automatic because the divisor is ample. But then, after a few steps, it will not stay ample. So it's really non-trivial that you can do this. And so I will say fact. Yes. Since minus kx is ample, there exists a choice of the Ri's in the MMP such that minus kxi dot Ri is positive for every I. Okay? And I will call this a special MMP. And then we have solved our problem because all the arrays now are k negative. So from now on, we always assume this, and it's very crucial. So So every Ri is k negative, and also this has a useful consequence. This also implies that for every I, xi has terminal singularities. So it turns out that k-negative things are nicer, and they preserve this type of singularities. So if you start from a smooth variety with k-negative contractions or flips, you always stay terminal. Otherwise, in the log Fano setting, we only have log terminal. Terminal is much better, okay? So this is, we settled the second problem. What about, what can we do about singularities, okay? Now, I want to consider, I have this birational map from X to Xi, the composition of all the sigma i's, and I want to consider an open subset here, which is over which this map is an isomorphism. Okay, so I'm sure that this open subset is smooth. So what I have to consider, what is the closed subset that we have to take out? It will be all the images of the exceptional divisors and all the loci of the small contractions, the indeterminacy loci of the inverse of the flips, okay, and all the transforms. So we consider this closed subset. So we set the first one, A1 in X1. It will be sigma naught of the exceptional divisor in the divisorial case. Yes? The xi? No, they are not smooth. X is smooth, but I did not hear the setup was always with X smooth. X is smooth, yes. And now I'm going to use it. Yes. Because, so I'm not sure I understood the question. No, no. For this, you only need Q factorial. Because you just intersect. You know that the ray is not contained in here, so you know that there cannot be any contracted curve in the divisor. So this gives that it is finite. And then to go from finite to fibers of dimension at most 1, you only need that di is Q Cartier. Okay, right. This is a good point. So here I implicitly use that xi for this, that xi is Q factorial. If you go back and look at the argument that I explained only in the smooth case. Because the fact that the dimension drops by 1 intersecting by a divisor holds when this divisor is Cartier or Q Cartier. Okay. Yes, so here I want to consider in the small case x1 minus the domain of the inverse of the flip. So this is the indeterminacy locus of the flips. This is the domain of the rational map, small case. Okay, so this is a closed subset. And then we do the same for every I, just by carrying the transform of the previous AI. So for every I from 2 to R, AI in Xi will be the image of AI minus 1 union the exceptional divisor if sigma I minus 1 is a divisorial contraction, or again, the indeterminacy locus of the flip union the transform of the previous bad closed subset. Okay, so if sigma I minus 1 is flip. And then xi minus ai is isomorphic to an open subset of x, by the composition map. And then it means that the singular locus of xi is contained in ai. So this is just long to write, but easier. Just the image of the exceptional divisor or the locus of the flip. And now we also observe that this ai is always contained in our prime divisor di. Let's see this for I equal 1, and then it's the same. Okay, so for instance, if sigma naught is divisorial, then remember that we have this assumption that D naught has positive intersection with the extreme array. So it means that D naught intersects every contracted curve, so intersects every non-trivial fiber. So its image must contain the image of the exceptional divisor. So D1, which is sigma naught of D naught, contains sigma naught of the exceptional divisor, which is just A1. And then in the case of the flip is similar. So if we have a flip, here we have D1, which is a transform of D naught. And again, D naught has positive intersection with the small array. Here, D1 has negative intersection with the small array because it changes the sign. So the exceptional locus of this small contraction is contained in D1. Okay, and this is exactly A1. This is what we are taking. This is exactly A1. The locus of the flip. Other questions? Okay. So for every I, we have that the singular locus of xi is contained in ai, and this is contained in di, and this is in xi. Okay, and then let's go back. We want to study the case where Ri is not contained in N1 of the ixi, and we have this contraction. And we said that this is a k-negative birational contraction. Let me write here, k-negative birational contraction with fibers of dimension at most 1. And we also say that xi has terminal singularities. And maybe I did not repeat this, but every xi is q factorial because this is included in our definition of log Fano. Okay, so we are only working with q factorial varieties. And also, so this is phi. And phi is finite on the divisor di. Okay, this is the information that we have. Okay, and now we use a result we use a theorem which is somehow a version of this result that we saw on contractions with one-dimensional fibers. Okay, so this is elementary. Which is a version for the singular case, of course, with a weaker statement. Okay, and it's due to Mori in the three-dimensional case, and then it was generalized by Shioko Ishii in, I think, 91. Yes. Okay. And the theorem says that in this setting, if we take an irreducible component of a non-trivial fiber, if F naught is an irreducible component of a fiber of phi, and it is not contained in the singular locus, such that F naught, then the intersection with the anti-canonical class is at most 1. Let me comment on this statement. So we know that this is also positive, because by assumption, I mean, here the theorem has the assumption that the contraction is k-negative, but it may be rational, because here we don't know that the canonical class is Cartier. So it could be, for instance, 1/2. And yes, the assumption, in fact, I think they have a weaker assumption that we don't need. I think that it is that F naught contains at least one point where the canonical class is Cartier. But this is enough. Okay, and then we are going to use this, which is weaker, but it's enough for our purposes. Because now let's take this F naught. So since the map is finite on the I, it is not, this curve cannot be contained because it's a component of a fiber of phi. So it's not contained in the singular locus because the singular locus is contained in the divisor, so we can apply the theorem. Okay, and moreover, we also have that F naught is not contained in AI, so it is contained in this open subset, which is isomorphic to an open subset of X, so we can take its transform in X. So this will be an irreducible curve in X. And then there is another point that I'm going to use that without proof, that if we compare the two anti-canonical degrees, of the transform in X and of the curve in Xi, we always have an inequality. Let me comment a little bit on this. This really depends on the fact that we have chosen all the rays to be k-negative, okay? And you have to, at least I think of this as a sort of compensation, because the flips, for instance, they create these curves which have positive intersection with the canonical class, but there is a sort of compensation that for the other curves, the intersection with minus k either stays the same or it increases, okay? And in fact, we have a more precise statement that strict inequality holds if F naught intersects AI, okay? So if you have a curve which touches the locus where the map is not an isomorphism without being contained in the locus, then its anticanonical degree strictly must increase. And this, in fact, is a more general fact than what we saw for the blow-up. We saw exactly the same for the blow-up in the first or second lecture for the center of the blow-up, and it was a special case of this. And then we are happy because we see that, so here we have x is smooth, so this is at least 1, and this is at most 1. So we must have equality. So from this, we see that we must have equality. And then we see that by this, F naught cannot intersect A. So this every irreducible component of every fiber of phi cannot intersect A. So we get this, let me write it here, for all the exceptional locus of the map. And then it means that this exceptional locus is entirely contained in the smooth locus. And then we are done, because it's like as if we were in a smooth variety. Okay, so we can apply, now we can really apply the results from the first lecture. So we can conclude that phi is divisorial. So it cannot be small, so in fact it's equal to sigma I. And it is just the blow-up of a smooth, irreducible, codimension 2 subvariety which is contained in the smooth locus of xi plus 1. And so the exceptional divisor of sigma I is a smooth P1 bundle and it is contained in the open subset where the map is an isomorphism. Because it does not touch this bad closed subset AI. So now this is the same because we saw that phi is divisorial. And so its transform AI in X is a smooth P1 bundle it's a smooth divisor with a P1 bundle structure. And let me call the fiber small ei. And we have that the intersection with the fiber is -1. This is just a property of the blow-up of codimension 2. And D will have positive intersection with the fiber because in Xi, this fiber generates the extreme array. And also the class of this curve does not belong to N1 of the dx. So, yes. So this is D, and this is the P1 bundle. Okay, and we get this for each step where, for each step of the MMP where the ray is not contained in N1 of XD. So we get, if the codimension of N1 of the X was large, we get many of these divisors, and they are all disjoint, because at each time, each of these divisors is disjoint from the loci of the previous maps. So what do we get in the end? Yes? We used it in an essential way to say that the map phi, the contraction, had one-dimensional fibers. Okay? And not only, but also one-dimensional fibers, and that it must be finite on the divisor di. Okay? Because otherwise, yes, I think you can write examples where these maps are just different. You get flips or divisorial contractions of a different type. Okay? If the map is not finite on the divisor di, you mess up all the situation. And it can happen that there are steps like this, but they will not touch our divisors EI. Okay? Other questions?
Would the same argument work so far if X were just Gorenstein? Would the same argument work so far if X were Gorenstein? Or you really need it to be smooth?
Yes, so I studied this construction in smooth case, and a few years later, a PhD student of mine, Gloria Della Noce, she studied the case where you start with X Fano, Gorenstein, Q factorial, and terminal singularities. And it's similar, so many conclusions hold. Yes, but then you don't have, so you still get these pairwise disjoint divisors, but they have less properties, okay? And then for what concerns the final statement of the theorem, she does not get, so you do not get that X is a product if delta is at least 4, but you get a finite map onto a product. And then you cannot prove, so I also do not have examples, so maybe it is a product, but it's at that point you cannot prove that it has degree 1. No. Okay. Yes, other questions? Yes, maybe I can also comment on this fact that terminal and Gorenstein are both essential, at least for our approach. Because if you allow canonical singularities, you can have small contractions with one-dimensional fibers. Okay, then if we started with C0, which was the codimension was positive, or say at least 1 or 2, we get S, which was the number of rays which were not, the number of steps where the codimension drops, so this is C0 or C0 minus 1, pairwise disjoint, prime divisors EJ. So we have D and all these nice P1 bundles. And the property of being disjoint is really strong. Yes, okay. Okay, and now I want just to see how one proceeds from here, and I said that I will not prove the theorem. Okay, so every of these EJ is a P1 bundle, and the intersection with D is horizontal for the P1 bundle. Okay, and so it's easy to see that every curve in EJ will be numerically equivalent to a one cycle in this intersection, in this horizontal, plus a multiple of the fiber. So we have something like N1 of EJ will be generated by the class of the fiber plus the N1 of this horizontal subvariety. This is a general fact, and this is in EJ. And then we push forward in X. And we get the same. So this is generated by the class of the fiber plus the N1 of this subvariety in X. Okay, so I want to draw some conclusion on the dimension of this subspace now. So you see already from here that the dimension of this is at most 1 plus the dimension of N1 dx, because this is contained in N1 of dx, okay? And I want, in fact, to show that if we have at least 2 divisors, it must be smaller or equal than the dimension of N1 dx. So suppose that S is at least 2. So we have at least 2 of these divisors, so I can take another one, EH, which is this joint from EJ. And then every curve in here, for every curve C, curve in D intersected with EJ, we have that the curve will have intersection 0 with EH because they are disjoint. Okay? So the class of this curve belongs to the hyperplane orthogonal to EH in N1 of X. Okay, but the curve is also in D, so it also belongs to N1 of dx. I promised a lot of linear algebra today. Okay, and so we see, so this N1 of D intersected with EJ is generated by these classes. So we have that it is all contained in EH orthogonal. Okay, and so you see that we don't have many possibilities. Either the dimension of this is strictly smaller than the dimension of this, or okay. Otherwise, it must happen that this is entirely contained in the hyperplane, but this is not possible because N1 of dx cannot be contained in EH orthogonal because let's just look at that picture. These 2 divisors intersect. Okay, so it's impossible that D has intersection 0 with all the curves in EH, because otherwise they would be equal. And so we see that the dimension of N1 of the intersection is strictly smaller than the dimension of N1 of dx. And so from here we see that the dimension of N1 of EJ x is lower or equal to the dimension of n1 of the x. Okay? Oop, I have many. So now, so let's assume, if we assume that the Lefschetz defect is at least 2 and start with D such that its codimension is exactly maximal. Okay. No, 3. Okay. Then this will be at least 3. So we have at least 2 of these divisors, because remember the number of these special steps could be the codimension minus 1. Okay. And then we can do this argument. And then this was already a prime divisor with the minimal dimension, so it must be equal. And so we get a lot of these special P1 bundles, where again the codimension realizes the Lefschetz defect. Okay? And then we forget about our starting D, and we restart with one of these. So we replace D with one of these, say E naught. And we redo the same. And so we get one of these P1 bundles. And all these other P1 bundles, which are pairwise disjoint and intersect E naught. And then I will just, I will just sketch how one goes on to prove the theorem, but there is still a lot of work, actually. We don't, yes, we can, yes, we actually forget about the other one. We just take one and we repeat the process. You are right, they will be different because the other ones were pairwise disjoint. So this is somehow a machinery that produces a lot of P1 bundles. Yeah. Okay, and now I will just explain by words without writing. If you have 2 disjoint divisors that intersect a P1 bundle, you have 2 possibilities. Either they both intersect along fibers, or they both intersect horizontally. Okay? And then there is some work to show that up to replacing E naught with another one, you can reduce to the situation where these EJs intersect horizontally. So you have like E1, E2, E3, and so on. And now we assume that delta is at least 4, which was the assumption of the theorem, so I have at least 3. And then you use this to show that all of these divisors are products. So this implies that for every J, EJ will be isomorphic to P1 times a smooth Fano variety, included E naught. And
Because you prove it for E0, right? And I guess you can really do the same argument.
Yes and no. In fact, once you prove it for E0 with some work, I actually need for these ones. For these ones also to prove it, but it's not difficult to show it once you have it for E0, but it's slightly technical, so I'll not get into it. But you can think, so why these 3? So these are only horizontal, so they don't need to be sections. But one way to think of this geometrically is that if you have a P1 bundle with 3 pairwise disjoint sections, then it must be trivial, because they will be the point 1, 0, 0, 1, and 1, 1. And so this is more or less the same principle, and this is where the 4 comes, to have 3 of these. And okay, and then once you have these, you can use, you have really a lot of information on X, and you use all these divisors and the MMP to produce a morphism from X to T and from X to a surface, and then you have you show that this gives a finite morphism onto the product, and then you show that the degree is 1. So there is still a lot of work, but I would say that the second part is more classical, and this is the first part with this MMP is the part which is, I think, more the nicer part of the proof. Yes, other questions? No, okay. And so I think this is what I wanted to say about the case where delta, the proof of the theorem for the case delta at least 4. Yeah, maybe I can answer more to Genia's question. Just, I need really to prove that these ones are products. I don't want to replace again. And so there is an argument to show that I actually produce, using the intersection with these other divisors, I produce a morphism from E1 to P1, and then to show that it is a product. Okay, so I work directly here, but it's not.
I thought you showed that the eyes also realized the Lefschetz defect. So that why can't
Yes.
you replace E0 with E1? So they're the same market.
Yes, you are right. You are right. You are right. You are right. It's not because in fact there is a tricky part that I need these EIs to intersect horizontally. And I cannot prove this. I can prove this up to replacing E naught with another divisor, okay? So it's actually, yes. Okay, so I want to say something about the case where Lefschetz defect is 3. As I said, okay. So let's say if X is Fano, with Lefschetz defect 3, as I said another lecture, X does not need to be a product. But you can still apply the same construction. We saw that we still have at least 2 P1 bundles whenever we run this MMP. So you can do something and say the same construction gives a flat contraction from X to T, where T is smooth, Fano. It has dimension n-2. So this is a fibration in the Pezzo surfaces. And the difference of the Picard numbers is 4. So it's not an elementary contraction. Let me call it sigma. So if you want, in this case, in the simpler case, it would be the projection onto T. But here we only have this. So we don't have that X is a product. So it's a weaker statement. And this was in the same, somehow, together with the result on the case delta is at least 4. But then many years later, or some years later, we have in 22, we have a joint paper with Eleonora Romano and Saverio Secchi. where we show that, in fact, there is a structure, more structure here. So we give a structure theorem for the case delta equal 3. And I will not give the statement because it's long, but I want to give an idea. So basically, so in the proof of the existence of this map, I actually find it as a composition of some elementary contractions. But it's not, the composition does not give many information. Instead, what we do is we decompose it in another way. And so we show that there is a P2 bundle over T, which is the projectivization of a decomposable vector bundle. Okay, and this map factors. So Z is smooth and has the same dimension as X. And so here the Picard number increases by 1. And here the difference is 4. So here the difference is 3. So what is this map? Let's call it F. And F is the blow-up of 3 disjoint, smooth, codimension 2 subvarieties. In Z. Okay, so this is what makes the Picard number increase by 3. And the centers of these blow-ups are completely described explicitly here. There are two possibilities. Either they are 3 sections, and they are in fact the sections that correspond to the three summands, the projection onto the 3 summands. Or there is a second case where it's slightly more complicated. 2 has sections, and the third one is not. But in fact, what is nice is that the description is completely explicit in terms of the line bundles. So you have your T, you have a condition on these line bundles, which is equivalent to the existence of this X. Okay? So it's nice because it's a very constructive result. And this is what I was saying the other time. So if you have a knowledge of Fanos in dimension n-2, then you can just list the possibilities for X. Okay? And so in particular, if we are in dimension 4, T will be a del pezzo surface, so we can do this. So as a byproduct of this, we get a classification in dimension 4 for the case of Lefschetz defect 3. So let me just state it. Let me see. Yes. Yes. So Fano 4 false. So of course, if delta is bigger than 3, also they are classified, but they are only products of surfaces. And instead, in the case of delta equal 3, so that they have Picard number from 5 to 8. And so In these two cases, 7 and 8, I only have one possibility, which is a product, so it's not very interesting. So if rho x is 8, x is the blow-up of P2 at 3 points square. And if rho x is 7, x is the product of the blow-up of P2 at 3 points times the blow-up of P2 at 2 points. Okay. Instead, in the other cases, there are non-trivial families. So in Picard number 6, there are 11 families, 8 of which are toric. And in Picard number 5, there are 6 families. 2 of which, no, how many? 4 of which are toric. And we also get families with the moduli, with the formations, say. Yes, so maybe I will do another further comment on this result, which is on the history, because it's nice. So in fact, when I got this result on 2012 on the case delta equal 3, I thought that was it. So I thought it was not possible to say more on this case. And then with Eleonora Romano, during COVID time, we studied this special case, this last one. So Fano fourfolds with delta equal 3 and Picard number 5, a very special case. And by hands, we got a classification. And we noticed that there were all these blow-ups of P2 bundles over P2, in this case. And so we said, OK, let's try to generalize. And at the beginning, we started slightly like maybe dimension 4, but larger Picard number. And then we realized that actually the same, more or less the same proof could be adapted to the general case. And, but without doing that special case, I would have never guessed this statement. So it was very useful to work out a special case to deduce, to understand that there was a general structure. Okay, and maybe let me just conclude with a comment on what happens when delta is smaller than 3. So what I believe is that when delta is 0 or 1, there is not much to say. But for the case where delta is 2, I think we still have to understand whether there is a nice structure theorem on X in arbitrary dimension. So I have a result on this case from 2014, but the statement is very technical, so I will not give you. And I think it's not optimal. So from the point of view of studying higher dimensional Fano varieties with large Picard number, I think that the good strategy is to understand better this case, starting from dimension 4. So in dimension 4, I will talk about this tomorrow, I have a good bound on the Picard number for Fano fourfolds with delta equal 2, but I do not have a good understanding. So I do not have a classification, and I do not have a structure theorem. So I have properties, but cases. So I think the first step should be to understand well the 4-dimensional case, and then to understand if in higher dimension, I mean, what happens in higher dimensions. So this is just as a research direction. And OK, so this is what I wanted to say about the Lefschetz effect in arbitrary dimension. Tomorrow, we will talk about somehow the properties of Fano varieties with large Picard number, and we will focus on the 4-dimensional case. So we will see, I will try to explain how one can classify Fano fourfolds with large Picard number, also applying these results on the Lefschetz defect. Okay, so thank you.